welcome to my channel. Welcome to your physics class. So today I will discuss about capacitors. So in the this is part 2, and in the part 1 lecture we have discussed what is capacitance. That is, capacitance is basically the measure of ability of the conductor to store charge and electrical potential energy. So, and we have calculated the expression for the energy stored by the conductor, and we have discussed some important characteristic of the capacitors, that how to increase the capacitance of a conductor. So we know that in order to increase the capacitance of a conductor, what we have to do is we have to place another conductor having opposite charge. Okay, or a arc conductor, if you place it in the vicinity of the capacitor, then its capacity increases because the potential decreases, right? And we have also discussed that if you place a dielectric material in the vicinity of the conductor, then its capacity also increases. So in the if you place a conductor or a dielectric material, then the capacitor, the capacitance of the capacitor increases. So that we have to do, that we already know. So keeping these facts in your mind, because when we are going to construct a capacitor, we have to keep in this mind that we have to make it in such a way, constructing in such a way so that the capacity of the capacitor increases, right, as much as can, so that it can store more energy and more charge in it. So capacitors is the it's a device that can store energy, so that is very much beneficial, because we all always our motive is to store energy so that we can reuse it, right? So now again I'm going to start from the very basics, so that we can brush up all the topics in a briefly, that we have already discussed in part 1, that is definition of a capacitance. That is, you can see here I have drawn, there are two plates. You can see one plate is made positively charged and the other plate is made negatively charged, and these two plates are keeping a distance apart, which, and the space between these two plates are filled with a dielectric material. Dielectric material means insulators, right? So the non-conducting materials, you can see. So if you take two metal plates, okay, having opposite charges on the surface of it, and if you keep it a distance apart, and if the space between these two plates are filled with a non-conducting material, so this whole arrangement is called capacitor. Okay, because you can see why we are putting another, we are taking two metal plates, because as I have told you that to increase the capacitance of the conductor, you have to place another conductor. So here the plate B, or the plate B is your another arc conductor that will increase the capacitance of the conductor A, right? So so here suppose here this is suppose plate A, and this is plate B. So plate A, suppose it has a capacitance C1, so that capacitance will be increased if you place another capacitor in the vicinity of it, and if you fill the gap by a dielectric or non-conducting medium, so that will also help you in increasing the capacitance of plate A. So we know the definition of capacitance, that is we know that if you increase the charge, so the potential of the conductor increases. So Q is proportional to V. That we have also discussed, that if you pour more and more water in a vessel, so the level of the water rises. So here also you can use the analogy that if you put more and more charge on the conductor, its potential get increased. So charge is directly proportional to the potential. The proportionality constant is the capacitance or capacity of the conductor to store charge or electrical potential energy. So that is C, that is represented by C, and so C is equals to Q by V. So now what is the unit of the capacitance? That is 1 farad. 1 farad is equals to 1 coulomb by 1 volt. So farad is a very large unit, as I have told you already, that that is so let me clear all the drawings first. Okay, now moving to the next slide. Okay, so more about capacitance. So capacitance will always be a positive quantity. The capacitance of a given capacitor is constant. So if you don't, if you keep it same, yeah, for different capacitors, you will have different capacitances. So next is the capacitance is a measure of the capacitor's ability to store charge that I have already discussed. And next is the unit of the capacitance is farad, which is quite large. So typically what we use practically, that is picofarad or microfarad. So now moving to the next slide. So here we were there you can see the arrangement of a capacitor. So that is called parallel plate capacitor. So here you can see that there are two metal plates. Okay, so let me name the two plates first. So suppose this is plate A and this is plate B. So you can see here that the plate A is connected with the positive terminal of the battery and plate B is connected to the negative terminal of the battery. So first we have taken two uncharged metal plates and we have connected them with the positive and negative terminal of the battery, and the space between the plates is filled up with some dielectric material, that is non-conducting material. So fine. So charge cannot flow between plate A and between A and B. So now what will happen then? See. So plus Q amount of charge is placed by the battery on the plate A, and plate B contains minus Q amount of charge. So each plate is connected to a terminal of the battery, right? The battery is a source of potential difference. Now here you can see the potential difference of the battery is delta V. Okay, delta V here, right? Now so and these two plates are kept at a distance small d, and the area of cross section of the two plates, the area of the two plates are capital A, right? So this is the area of the two plates. So and we assume that these two the area of the plates is much greater than the distance between these two plates. Okay, so capital A is much greater than small d. Why I am saying so, I will tell you later. So here you can see that we have defined, so plus Q amount of charge is placed on plate A and minus Q amount of charges on plate B. Now so what is charge? Now I have told you that charge is continuous, discrete, right? We define a charge by integral multiple of electronic charge. Q is equals to plus minus Ne. Now we know whenever we are talking about charge distribution, okay, so if there are closely spaced charge placed on a conductor, so it seems a continuous charge distribution. So whenever we are talking about continuous charge distribution, if it's a surface, if it's a plane surface, 2D surface on which the charge is placed, so then we have to use the parameter called surface charge density. If it's a volume, then we have to use volume charge density. If it's a wire of carrying positive charge or negative charge, whatever it is, then we have to use the parameter line charge density. So here you can see I have denoted sigma. This is basically sigma. Okay, so sigma is equals to Q divided by area. So total charge on the plate divided by the total area of the plate, that is the surface charge density. So fine, so we have defined surface charge density. Now so sigma is Q by A. Now next is we are going to calculate the electric field, because here you can see there is a positive charge and negative charge, same amount of charge, but they're opposite charges and they are separated by a distance d. So there will be an electric field between plus Q and minus Q, and the electric field direction should be from positive charge to negative charge. Now we will calculate this electric field. So before going to calculation, so we cannot, here I have already written the electric field's value, which is sigma by 2 epsilon naught, but now I will give you the I will calculate it. Okay, so let us calculate first how to let us see first how to calculate the electric field intensity due to a plane sheet of charge. So from that you will understand this expression very easily. So let us start, let me start the whiteboard with you, then share whiteboard, then I will discuss. Okay. So suppose there is a plain sheet of charge. So it's a plain sheet of positive charge. Now we are going to calculate the electric field intensity here, right? So what we have to do is we will take a cylindrical Gaussian surface. Okay, cylindrical Gaussian surface. Okay, so now so we know that the electric flux, right? The electric flux phi is equals to the electric field intensity into area. Suppose the area A is the area of the plane sheet of charge. Okay, and this is the electric field. Suppose if you put a positive charge, unit positive charge here, so it will feel a repulsion in this direction, Coulomb's repulsive force. And if you put a positive charge here, so it will feel a electrostatic force of repulsion in this direction. So that is E arrow. So phi is basically E into area, right? So that is equal to, according to Gauss law, that is equals to Q enclosed divided by epsilon naught, right? So here the total charge enclosed is Q by epsilon naught. So the total charge is on the, so Q is the total charge on the sheet, that is sigma into area, right? We can also replace Q by sigma into A. Sigma is the surface charge density multiplied with the total area, right? So that is the total charge placed on the surface. So now here I will introduce a factor 2. Why? Because this plane sheet of plane sheet of charge, it has two surfaces, right? So on the back there is charges, and on the front face also there are charges. So that's why we have to introduce this factor 2 here. So from this expression, if you equate, so A cancels out, so it becomes sigma by 2 epsilon naught. Okay, so that is the expression for a plane sheet of charge electric field intensity due to a plane sheet of charge. So here you can see that that I was discussing, that E is equals to sigma by 2 epsilon naught. Okay, now here in this picture you can clearly see that I have shown that the electric field is 0 on the plate A and plate B. Only the electric field exists between the plates. Okay, and elsewhere it is 0. And inside the plates, in the gap between the plates, the electric field exists, and its value is sigma by 2 epsilon naught, that we have calculated. Now the electric field on the plates is 0, or on the above or below the on the left side of the plate, on the right side of the plate, electric field is 0. Why it is so? That we will calculate. That I will show you. So suppose, okay, so suppose there are two sheet of charges. Okay, so this is also positively charged, and this is also positively charged. Okay, now these two plates, you can see it divides the space, the whole space, into 3 regions, right? Region 1 is the region on the left side of the this is suppose plate A, and this is plate B. So plate region A is left on the plate A, and region 2 is the region sandwiched between these two plates A and B, and region 3, you can see it's the right side of the plate B. So you can see that if you place a positive unit positive charge here in the region 1, so it will feel a electrostatic repulsive force due to plate A, right, and due to plate B also. right? So suppose this is, the surface charge density in plate A is sigma A and surface charge density on B is sigma B. So this is EA and this is EB. So both will be in this direction. So if you add up, so then the net electric field intensity in region 1 is EA plus EA arrow plus EB arrow, because both are directed in the same direction. So this is basically 1 by 4 pi epsilon naught, which is K, right? Sigma A plus sigma B. Sigma A plus sigma B, right? So here instead of K, sorry, so this is basically, we know that the electric field intensity due to a plane sheet of charges is equals to sigma by epsilon naught. So here you can write that 1 by epsilon naught sigma A plus sigma B. Okay, sorry, there is a 2 factor comes up. So now if you consider a point charge here in the region 2 in between plate A and B, so it will feel a repulsive force due to sigma A in this direction, and due to this sigma B of charge, it will feel a electrostatic force in this direction. So here EA and EB are not directed in the same direction, they are oppositely directed. So for them, what will be the resultant, what will be the resultant electric field intensity? That will be minus. So net electric field intensity in region 2 is EA minus EB. So that is sigma A minus sigma B. Now if sigma A is greater than sigma B, then it will be directed, the net resultant electric field intensity will be directed in this direction, away from plate A. And if sigma B is greater than sigma A, then it will be directed away from sigma B. Now we will talk about region 3. So for region 3, region 3, so what will be the direction? See, in region 3, if you take up unit positive charge here, so it will again feel electrostatic repulsive force due to sigma B in this direction, and for sigma A also it will feel a electrostatic repulsive force in this direction. So here also EA and EB are directed in the same direction. So here also E3, right? So the net electric field intensity in region 3 is EA plus EB. So that will be 1 by 2 epsilon sigma A plus sigma B. Now if sigma A and sigma B are equal to sigma, right? If the magnitude of the surface charge density on both the plates are same, and if they are oppositely charged, suppose this is positively charged and this one is negative charge, okay? So this one is negative charge instead of positive one, okay? So then what will happen? Then we can write that sigma A is equal to sigma B is equal to sigma, right? So sigma A is equal to, sigma A is equals to minus sigma B. So if you put in region 3, right, instead of sigma A, if you write minus sigma B, so that will be 0. Again, in the region 1, if you put instead of sigma A minus sigma B, that will be 0. But in the region 2, but that is sigma A minus sigma B, if you put the value, you will get 2 sigma A or 2 sigma divided by 2 epsilon naught. So that will become, in region 2, the net electric field intensity becomes sigma. That is sigma is equals to sigma, B is equal to sigma. So that is sigma by epsilon naught. So the electric field intensity in between these two plates is sigma by epsilon naught, right? And on the left side of plate A or right side of the plate B, electric field intensity is 0. So now we will, discuss from the PDF. So here you can see that I have written that if the capacitor is initially uncharged, the battery establishes an electric field in the connecting wires. And we have already shown here that the above the plus Q or plus sigma that this sheet is containing plus sigma charge, above which electric field is 0 and below which electric field is 0. In between the electric field is non-zero, which is, now the value is definitely sigma by epsilon naught. Okay, so now next is parallel plate capacitor, that this field applies a force on electrons in the wire just outside of the plates, right? So the force causes the electrons to move onto the negative plate from, right? So this continues until equilibrium is achieved, that both the potential difference between the plates become equal to the potential difference of the battery, right? That is called the equilibrium condition. So at this point, there is no field present in the wire and the movement of the electrons ceases. Okay. So here these topics we have already discussed. The sigma is equals to Q by A. A is the area of each of the plate. Q is the charge on each plate, and the electric field is uniform between the plates and zero everywhere, right? Zero everywhere, and it is uniform between the two plates A and B. And we know that here we know that the let me on the annotation. Okay. So we know that the uniform electric fields are, they are represented by parallel electric field lines, equispaced, and so there are uniform electric field inside the, between the two plates. Okay. Okay. Let me just give me a minute. Okay. So now you can see that what we have done here is capacitance. Okay, so capacitance is proportional to the, now we are going to calculate the capacitance of the parallel plate capacitor. Here we can see that we have already calculated the potential difference between the two plates. Now, sorry, we have already calculated electric field, right? That is sigma by epsilon naught. Now we are going to calculate the potential. So we know that the potential difference is minus E dot ds, right? So, and delta V is equals to basically E into D. So D is the distance between the two plates. So we have calculated the value of E, which is sigma by epsilon naught. So put the value here, then your potential comes, and then put the, and we know that capacitance is Q by delta V. So substitute the value of delta V here, then you will get the capacitance for parallel plate capacitor, which is epsilon naught into area of the plate divided by the distance between the plates. So you can see that if you increase the separation between the plates, then the capacitance increases. No, the capacitance decreases, right? Inversely proportional. So if you increase the separation, capacitance will decrease, and if you increase the surface area of the capacitor, then the capacitance will be increasing, right? Now moving to the next slide. So now we will talk about cylindrical capacitance. Okay, so here, so already we have discussed parallel plate capacitors. Now we will talk about cylindrical capacitors, spherical capacitors. So what are they? So basically, if you take two conducting cylinders. Okay, here you can see the pink one is a solid cylinder of radius A. Its capacitance is suppose C1. Okay, and it has been put inside a hollow capacitor of hollow cylindrical, cylindrical shaped metal. Its radius is B. So they are concentric cylinders of radius A and radius B, and it has capacitance C1 and C2. So they are basically two plates of capacitor, two plates. So suppose the plate 1, that is the cylinder placed inside, that is suppose plate 1, and the outer one is plate 2. Now you can see the plate 1, it has a radius A, and plate 2 has a radius B. Okay, so what we have to, suppose plate A is positively charged and plate 2 is negatively charged, and the space between these two plates is, it's empty, so it's filled up with air, which is an insulator, right? A dielectric medium, non-conducting medium. Now what we have to do is, first we have to calculate the electric field inside the space between the two plates of the conductor. So for that, what we have to do, again we have to consider a Gaussian surface. So we know that here the electric field intensity has a cylindrical symmetry. So that's why we have to consider a Gaussian surface of cylinders. Its shape it should be cylinder. Now the radius of the cylindrical Gaussian surface is suppose small r. Okay, so now we apply Gauss's theorem to calculate the electric field intensity inside these two plates, inside the capacitor. So that we can easily do, we know how to do it. So here you can see that the flux is, use Gauss's theorem, that closed line integral, surface integral E dot dA arrow is equals to closed surface integral E dA is equals to Q enclosed divided by epsilon naught. So here, what is the area? Area of the cylinder is, surface area is 2 pi RL. So E into 2 pi RL, that is the surface area of the Gaussian surface that encloses the charge, which is Q in. So Q inside is lambda into L, because here we have considered line charge density. So lambda is the line charge density that should be multiplied with the finite length of the cylinder. So lambda L is the total charge inside the Gaussian surface divided by epsilon naught. So here you can see, so the total if you take the this factor on the right hand side, then it becomes E is equal to lambda by 2 pi epsilon naught into R. So they have taken this 1 by 2 pi epsilon naught term by 2k replaced, so into lambda by R. Lambda is the line charge density and R is the radius of the Gaussian surface. Now we have already calculated the electric field intensity inside the capacitor. Now we are going to calculate the potential difference. Then we will calculate the capacitance. So see the steps. Okay. So in order to, whenever you are asked to calculate the capacitance of any system, what you have to do is first calculate the electric field intensity inside the capacitor, then calculate the potential by using the relation between electric field intensity and potential, and then calculate the capacitance, that is C is equals to Q by V. So here you can see that delta V is equals to minus integration A to B E dot ds. Here we have to take the radius RA to RB, right? RA is the radius of the kind of plate, the plate 1, and RB is the radius of plate B. So and we have placed the value of the electric field intensity, so that is lambda by R into dr. So we are going to integrate it over the radius. So the result will give you, it will be like minus 2ke into ln b by a. It's a very easy integration. I hope all of you can do it. Okay, so this is basically multiplied with ln b by a. So lambda is Q by L, that we know, that is the line charge density, and here the capacitance, so that is C is equals to Q by delta V. So put the value of Q here, that is lambda into L, and put the value of delta V here, so it will come L by 2ke ln B by A. Okay, so that is the capacitance of the cylindrical capacitor. Okay. So now we will move to the next topic, which is spherical capacitor. Okay. So in case of spherical capacitor, again you can see there are two concentric spheres. Okay. So this is, suppose this is called, so this is suppose plate A and this is plate B. They are concentric. Its radius is A, its radius is B. So what we have to first do, that we will calculate the electric field intensity inside the inside these two plates, inside the capacitor. So what we have to do for this, we have to use Gauss's theorem. So we will construct a Gaussian surface that should be here, that should be a sphere of radius r. Okay, a sphere of radius r. Okay, and then again we will when we will calculate the potential, we will integrate it over the the initial limit should be small a, and the ultimate final limit should be b. right? Upper limit should be B. So if you integrate it, you will calculate if you calculate the potential, that will come KEQ 1 by B minus 1 by A, right? So here I have already shown here the calculation of the potential, and electric field is definitely KEQ by R square. So I guess all of you are able to calculate this electric field intensity, though I can show you here. See that E into the flux is E into area. Here the surface area of the Gaussian cylinder is, Gaussian sphere is, that is 4 pi R square, that is equal to Q enclosed divided by epsilon naught, right? Okay. So if you divide it, then it becomes 1 by 4 pi epsilon naught Q by R square. So this 1 by 4 pi epsilon naught is your K, and that small q is basically, here they have considered capital Q and R square. So I guess all of you have clearly understood this. So then they have calculated the potential minus integration E dot dr. So that is the result of the potential difference between these two plates. So now you can easily calculate C, which is Q by delta V. So that is AB by KE B minus A. Okay. So I guess all of you have understood these topics clearly. Okay, so this is the circuit symbols. Capacitor symbol is we just this is the symbolic representation of a capacitor. Two parallel lines, and these two are connected. This is a symbol that this suggests that they are connected with the battery. And battery symbol is, right, we know there's a switch on and switch off symbols. Okay. Okay, now we will talk about capacitors in parallel and capacitors in series. Okay, so capacitors are in parallel when they are said to be in parallel condition when the potential difference of these two capacitors will be equal, and the charges on the capacitors will be different. So these two capacitors, you can clearly see that C1 and C2, these two capacitors are connected parallelly, and the plate 1 of C1 and the left side plates are connected with the positive terminal of the battery, and the right side are connected with the negative terminal of the battery, and Q1 is the charge on the capacitor 1, and Q2 is the charge reside on capacitor 2. Now we will calculate the equivalent capacitance. So if we replace this arrangement by equivalent capacitance, then we will calculate the and if we calculate the the equivalent capacitance, then what we will have. So here you can see the potential difference between the battery is delta V. So between the plates are also delta V potential is there. So potential is same. So we can write that delta V1 is equals to delta V2 is equal to delta V. And the total charge on the system is, on the capacitor is, Q1 plus Q2. So if you there is another capacitor C3 here, you can see. So if we replace these two capacitors connected in parallel by an equivalent capacitor, which is written as C equivalent, that is equal to C1 plus C2, so that then the potential difference between these two plates is delta V, that is the potential difference of the battery. So here we can write as Q is equals to Q1 plus Q2, and delta V is equals to delta V1 is equal to delta V2. So here on the above, you can see the calculation that C equivalent is basically Q by delta V. So Q is basically Q1 plus Q2, delta V is delta V1. If you write it as Q1 by delta V plus Q2 by delta V, and delta V is equal to delta V1 is equal to delta V2. So instead of delta V, you can write delta V1 in this case, and here you can write delta V. Instead of delta V, you can write delta V2. So Q1 by delta V1 is C1, and Q2 by delta V2 is C2. That we already know. So from here we can clearly see that C equivalent is the algebraic sum of the individual capacitors. So C equivalent is always greater than any one of the capacitance of the capacitors. So C equivalent is C1 plus C2 plus C3 and so on. So the equivalent capacitance of a parallel combination of the capacitors is greater than any one of the individual capacitors. So essentially the areas are combined, Now the capacitors in series. Okay, so now if we talk about two capacitors connected in series connection, so then definitely the potential differences are not same, but what is same? The charges are same. So Q1 is equal to Q2 is equal to Q, but potential difference is delta V1 and delta V2 for both the capacitors. So now if we replace the whole arrangement by a equivalent capacitor, so what we will see is, and if we calculate it, so we can see that C equivalent is Q by delta V, which is delta V is delta V1 plus delta V2. So if you take the reverse or inverse of C equivalent, so 1 by C equivalent is delta V by Q. Now see, delta V is delta V1 plus delta V2, the algebraic sum of the two potential differences, that should be equal to the potential difference of the battery. So instead of delta V, write down delta V1 plus delta V2, and instead of so basically it is delta V1 by Q plus delta V2 by Q. Now Q is equal to Q1 and Q2. The charges are same. So instead of Q, you can write here in the first term, write Q1, on the second term, write Q2. So it is basically, 1 by C1 and 1 by C2. So C equivalent here is equal to 1 by C1 plus 1 by C2. So here you can see that the equivalent capacitance is, the equivalent capacitance of a series combination is always less than any individual capacitor in the combination. So today we will just, this is all about capacitors. In the next video, I will talk about the when we place dielectrics inside the capacitor, different dielectrics having different dielectric constants, then what are the results. So we will continue this chapter, and thank you for watching my video. I hope this video is anyway helping you in studying capacitance. Thank you. So thank you for watching my video, and please, if you like the video, please share with your friends, and if you want to suggest any suggestion from your end, please give a comment, write a comment in the comment section, and please let me know that what are the doubts you have. So write down in the comment section so that I can clear those doubts in the next video. Thank you, and thank you for encouraging me, so for making these videos and taking classes online. So that's a very happy moment for me, for your support. You have already have a very greater subscribers. Thank you for all.